In order to understand what adaptive approximate significance in image processing can achieve, it's essential to understand how image processing is currently performed. I'm going to use this Certosa.io site to explain this, and I'd recommend anyone to visit the site for further experimentation. This image shows a small area of a larger image, with the grayscale matrix on the left, representing the pixels of the image in the center, and a smaller cutout image to the right. This next shot shows the 3x3 convolution kernel we're going to apply to the image on a pixel by pixel basis. The kernel is applied to each pixel from top left across to the top right. This is then repeated for every subsequent row from top to bottom. This next area shows the multiplication and addition operations between the pixel of interest plus the surrounding pixels and the 3x3 kernel. So for each pixel shown on the right here, we have a number of there will be 9 multiplies and 8 additions, which I'll term this as 8 max, or multiply accumulate operations, in order to produce one process pixel result on the right hand side image. So there we see the 22 in the red area on the right and the 9 pixels 3x3 on the left hand side. This kernel could also be a 5x5, 7x7 or 9x9, etc. But generally the higher order kernels can give more accurate results but involves more multiplies and additions. This image shows a 3x3 image applied to the cedar waxwing image by Raymond Lavoie. This is a background image from the Ubuntu installation. You'll see it a few more times as we go through this presentation. This image is a 2560 by 1600 or 4.1 megapixel image. Convolving this whole image represents about 33 million max. This spreadsheet calculation shows a relationship with some typical image sizes and the number of max for 3x3 and 5x5. So as we move from these typical sizes up to the 4K and 8K images, we will see exponential growth in the max calculations and also in the energy consumption. Right, by using a locally calculated deviation, this demonstrator illustrates the image significance and compares a relatively expensive standard deviation computation, which includes squares and square roots, against absolute deviation and an approximate absolute deviation, where one pixel in each of 4x4 sub-areas is selected and used to generate a local deviation along with other local samples. So as we vary the threshold, down this side we have the standard deviation, absolute deviation, and you see that immediately our brighter area disappears in each one, and you get much the same sort of processing with each one. So as we increase each one, so the standard, the absolute and the approximate, you can see we get the same sort of results, but the computation involved with the approximate is far less because you're only using about a 16th of the processing of the whole image. This is a fairly large image, 2560 width by 8. So as we go up the scale, the threshold scale, you can see that the most significant parts of the image, which is the bird's head and parts of the branch that it's sitting on, offer the greatest deal of significance level. So this is what we can play on in the next part of it. So now we move on to adaptive approximate image significance. So by using 2 separate threshold levels, we can easily classify areas of the image into 3 levels: low significance, or 0, where no processing takes place; medium significance, 1, where a 3x3 convolution is performed; and high significance, 2, where a more accurate 5x5 convolution is performed. This demonstrates the PPQ also has a PPQ slider, which is power, performance and quality, for selection. This allows the concept of selection of 5 varying percentage based processing levels, so you've got 0 to 4, and I've also got, this is for adaptive processing, plus an extra 2, 5 and 6 that illustrate the application of 3x3 or 5x5 across the whole image, so we just moved out to 5 at the moment. That is a 3x3 image applied to the whole thing, the whole image, which is what normally happens in image. See down here that the processing time is 17 milliseconds. The 3x3 kernel is a sharpened filter. The 5x5 is a first order Sobel filter. These chose merely to give an easily discernible 3x3 and 5x5 result for this demonstration. So if we look at that's the Sobel filter. So you can, when we now look at the adaptive stuff, we can easily tell that there is the Sobel filter, or that 5x5 applied to the bird's beak, and the 3x3s to these other areas around, and with this occasional smashing of 5x5. So now we have a sort of dynamic process where you can change the PPQ level and change the amount of processing. So you see the two threshold values vary as I wind them up, and up here at the top of this image you have 3 target levels, which is 800 blocks for no processing, 100 blocks for level 1 processing or 3x3 filters, and 100 for 5x5. The next one is an average of what the processor, the software is achieving, or the nearest value. So we can actually select 4x4, 8x8 or 16x16 areas to generate this average, the approximate sig size on. That ends up reducing the 2560 columns and 1600 rows to an approximate significance matrix size of 640 by 400 in this case. So we're working with a smaller processor for the average. These values are then grouped into a 32x32 or 64x64 work group. This is to align with GPU and Neon processing. And the grouping enables approximate significance to be pulled into a smaller matrix for threshold level selection. So here we can see that we've got 40x25 or a total of 1000, which is quite handy for looking at these values so that you can relate them to percentage wise. You can see that here we're looking at 80% no processing, at 10% at 3x3 and 10% 5x5. And this information printed up here. Also on the image you have the CPU frequency, but we'll show this in a separate video section later on because that only runs on the XU4. So the target. So we've got these two tellbacks at the top and the bottom, so we can see what's going on. The other thing we have here is the processing time and the slack time. Now the slack time is the amount of processing time we have available for other things, and this will be looked at in the next section, the later section where we look at the XU4 stuff, but I'll have to video it in a different method. So as we go up in the PPQ level, you can see that more and more parts of the image get processed at 5x5 and more at 3x3. So and of course all this time the processing time is going up and slack time is coming down, but we still have 79 milliseconds of slack time here. Now the other option later on which we'll see is where you can, once you can go down to this lower level, you have a significant amount of slack time, so we have the opportunity of reducing the CPU frequency, which won't happen on this, but it happens on the later domain. Right, now we move on to some real image processing, looking at a couple of test videos. The following is an OpenCV short test video sequence that demonstrates the power of this process. I need to point out that there is no image tracking involved other than the image significance process itself. As we shift the PPQ down, you see the there's less sections being tracked, but processing time goes down and slack time goes up. And you can notice that as more people come into the picture, that the actual threshold moves up and down with the activity. If this was linked with the CPU frequency, it could be quite attractive. Okay, now we move on to a live camera feed into the Odroid XU4 board. So we've got camera looking out to the window at the there's a road along here with obviously traffic moving along it, and today we have some sheep in the field, so we'll see if we can pick them out. So if I get rid of this image file now, and here we have our usual image significance with the adaptive processing. So it's picking the cars up going along the road. We're at the lowest level here, which is 0 for minimum power and lowest quality really. So if we move the quality up, we'll see we've got more 5x5s coming in, certainly picking up all the cars along the road as they move along. And some of the sheep are starting to get picked up as well now in the field. Normally all this area around here in the field is ignored because normally the sheep only just come back in overnight. So as we go up to the higher levels, so we get more and more processing. Now the slack time has gone down to 32 milliseconds here, but if we wind this back down to the lowest quality, the least power, so this will home in on the it'll be about at the requested levels, and we've got a 30 millisecond slack time. So if I now start moving CPU frequency down, we have 18 selections, and you see up here we have 2 gigahertz on the processor, and as we bring this down, the main thing to notice is eventually the slack time will start moving down towards 10. When we get to about 10, that's about the limit of as far as we go, because there are, with Linux, there are other things going on in the background, and it can go into dropping frames once you get around 10 milliseconds. So it's still doing quite well at the moment. Typically we can get down to about 600 megahertz without any dropping frames, and it's still picking things up there at the moment, but it's ignoring all the sheep, well, most of them. And then we're at 700 hertz down to 600 hertz, and it's still running fairly well in real time. And then we go down to 500 hertz, megahertz. And obviously the most significant thing it's looking at is the traffic and a bit of the vegetation in the foreground. So that is DVFS applied to image processing. Right, now we move on to looking at the power reduction with the slack time. Now we're going to use the Cedar Wax Wing running at 10 frames per second as a stable image to demonstrate the potential for power reduction by utilising slack time. This image is just a bit more stable than live video, but I have to multitask controlling 2 computers at once here. So the right screen shows the Texas Instruments INA 231 evaluation module. This is software running on monitoring the Odroid XU4 power. This also includes the Linux runtime power, so here we see the thing logging the power. Linux runtime power is typically around 4 to 5 watts on idle mode, but this figure can be factored out to get an estimate of the demonstrator application power usage, but I won't go into that here. as can be seen when running the 100% sober 5x5 convolution, we're in negative slack time down here and slower than 10 frames per second, so there's no potential for power saving here, and it's using around the 7.8 watts. Right, so if we go to 100%, we go down to the 100% 3x3, we see the slack time goes up to 29.7, so we could actually slow down the power just here a little bit. Go back up 6, around about 1600 megahertz, and we're showing a slack time of about 12 milliseconds, 10 milliseconds. I tend to use 10 milliseconds as the time, but you can see on the right hand side the power's dropped to about 5.9 watts. Obviously we can average these out and get much better results in a proper test. If I now go down to PPQ of 4, which is our most highest quality of the adaptive image processing, we now find we can go down here to about 1400 megahertz, and we're still in positive slack, but again we've got another reduction of power going down to about 5.2 watts. So I go down to PPQ3, and again we can drop the frequency because we've got positive slack time here. This time we're going to about 1300 megahertz, and the power has dropped to about 5.1 watts. And the next step is a further step down again. So here we're into PPQ2. We can shift the frequency down to 1100 megahertz, and we're still in positive slack time, and the power's dropped to about 4.8 watts. Step further, PPQ1. PPQ1, and we can drop the frequency now to 900 megahertz, and the power has dropped even further to about 4.5 watts. And then obviously PPQ0, there's the opportunity for this image, gets down to about 700 megahertz, and still staying slightly positive, and the power has dropped to 4.3 watts, and that's power saving with slack time.